Hi everyone. Today we're going to be looking at our notes for modeling with sine and cosine. I want to start off with this warm-up where we're going to write a sine and cosine equation that can represent both of these graphs here. So we'll start on the left-hand side. We're looking at this wave here. I'm going to start with my sine equation. I notice that my y-intercept starts at the midline, and the next time that we hit that midline that starts the cycle again is over here at 2 pi. So I know that if each increment is pi halves, then 2 of them should be pi, 3 of them should be 3 pi halves, and then 4 of them should be 2 pi. So I notice that we have one cycle between 0 and 2 pi. So writing the equation, we have y is equal to our a value, that amplitude is going to be determined by our maximum minus our minimum divided by 2. So we have our maximum of 5 minus our minimum of -1. So 5 minus -1 is 6, and then divided by 2 is 3. And then this is our sine equation. Our period we just found was 2 pi. That's the start and end of our cycle here is from 0 to 2 pi. So our b value must be 1. We're going to use our variable x. And then do we have a horizontal shift? No, we do not. So there is no addition or subtraction from the input. And then finally, that last piece is our midline. Our vertical shift is +2. Now we have to determine whether or not this is positive sign or negative sign. Well, because we are first going down from the midline, then this is a negative sign. Okay? Your answer may vary. Let's write a cosine equation. So y is equal to, the amplitude does not change, so we still have 3, and then cosine. Now we have to determine, again, our b value is our period. The period hasn't changed either. So we have x, and then let's determine where we're going to start from. So I'm going to start up here at negative pi halves, and I know that that cycle ends at positive 3 pi halves. So we're looking at from here to here. So if I'm starting at negative pi halves, that's a shift to the left pi halves units. So we're going to add pi halves to the input. Finally, that vertical shift determines our midline. That's our +2. Remember, the equation for the midline is y is equal to k, that vertical shift. So here are two equations. Again, your answers may vary. For the second graph here, we'll start with our sine equation. So here we have our start, and then our end, we'll say is right here. Well, each increment is pi halves, so that means the second mark is at pi, one more increment. And then we have our minimum of -3 and our maximum of +3. So we have our sine equation, y is equal to 3 sine. So 3 is that amplitude. We're going from 3 to -3. And then our period, we know that period is equal to 2 pi over b. Well, I know that the period for this function goes from 0 to pi, so we can solve the equation. Pi is equal to 2 pi over b, and solving for b, we get b is equal to 2. So we have 2x as our input. We're not shifting it right or left at all. We're starting at x equals 0, the y-axis, so there is no horizontal shift. And then there's also no vertical shift. Our midline is the x-axis, y equals 0. Now, is this positive or negative sign? Well, we're going down from our starting point. So from the midline, we're going down to hit our minimum. So this is a negative sign function. So here's our equation, y equals -3 sine of 2x. Our cosine equation, again, I'm going to start, well, I'll start over here at positive, on the positive side, and we'll talk about exactly what that x value is. The next time it reaches that point is over here. So we have y is equal to, amplitude hasn't changed, so we have 3 cosine, period hasn't changed, so 2x, and then we're shifted to the right some number of units. Well, I know that it's exactly in the middle of x equals 0 and x equals pi halves. Remember, our maxes and mins occur exactly halfway between our points on the midline, and vice versa. Our points on the midline occur exactly halfway in between, right in the middle of our maxes and mins. So then if this is right in the middle of 0 and pi halves, this x value here must be pi fourths. So we're shifted to the right pi fourths. Now notice that the argument of the cosine here, I'm writing in factored form. This must be in factored form. You do need these parentheses in order for this equation to be correct. And finally, our vertical shift, the midline is y equals 0. There is none. And then we have to determine whether this is positive or negative cosine. Because we're starting at a minimum, this is negative cosine. So here is an example for the equation, the cosine equation. Again, your answers may vary. Okay, let's move on to number 2. Identify the period of the function y equals 2 cosine of pi sixth x. Sketch one cycle. Okay, so I know that my b value here is pi sixth. So I'm going to go ahead and write b is equal to pi sixth. And I also know that the period is equal to 2 pi over b in radians. So then this must be equal to 2 pi over pi sixth. Well, when we're dividing out pi sixth, this is the same as multiplying by the reciprocal. So we have 2 pi times 6 over pi. Our pi's cancel, and we're just left with 12. So our period here is 12 units. So I know that this is a positive cosine function with an amplitude of 2. So I know that, and I also know that there's no vertical shift. So I know that my max and min will be 2 and negative 2, respectively. And then we also have a period of 12. So we're going from 0 to 12. Halfway in between 0 and 12 is 6. Halfway in between 0 and 6 is 3. And halfway in between 6 and 12 is 9. So these are our 5 key points, 0, 3, 6, 9, 12. And then I'm going to graph the positive cosine. So we start at the maximum, we hit our midline, we hit our minimum, back to the midline, and then finally end at a maximum. Sketch that graph. Don't forget to curve those ends downward. We don't want to exceed those maximums. And we have one cycle here. Okay. Draw those arrowheads. This does extend infinitely in both directions. It's a periodic function. Okay. All right, so now I want to take a look at the Ferris wheel example. The goal here is to figure out where will the red car be at the end of the ride. Okay. So here is the example here. We know that this is a 3-minute ride and the red car begins at the bottom. So what types of things do you think we need to know in order to answer this question? Okay, see if you can brainstorm a few things and then write them below. A few things that I'm thinking. So some things that we need to know, we would need to know, one, we'd have to know maybe like the period of one rotation. Okay, so if I'm just rotating once around the Ferris wheel, how long is that going to take us to complete one rotation? I also need to know, like if I want to know where the car is going to be, I need to know exactly where it's at right now. So at the start of the ride, I need to know the height of the Ferris wheel from the ground, I'm going to say the bottom, and I'm also going to say the top. I need to know the diameter of the Ferris wheel. So I need to know the height of the bottom and the top of the Ferris wheel from the ground. I need to know if the bottom of the Ferris wheel is 2 feet off the ground, 10 feet off the ground, and if it's a 50-foot Ferris wheel or maybe just a 10-foot Ferris wheel, something like that. Okay, that's going to help me determine exactly the position of that red car at the end of the 3-minute ride. Okay. All right, so now let's take a look at the example. So you can follow along with me. I'm going to pull up this video here. Okay. So let's take a look. I'm going to play this video and just follow along with me and just observe what do you notice is going on in this video. So I'm going to hit play. All right. So take a moment and just jot down your observations. Remember that it started at the bottom and it's a 3-minute ride. So this is just the first 15 seconds of the ride. Okay. So let's take a look back at our notes. So again, here's the starting position. There's a few things that we need to know. So I'm going to give you some information. So given 2 things. 1, the bottom of the Ferris wheel is 9 feet above the ground. Okay, the bottom of the Ferris wheel is 9 feet above the ground. So this distance here from the ground to the Ferris wheel is 9 feet. Okay. The second thing that you need to know is that the Ferris wheel is 50 feet in diameter. It's 50 feet in diameter. So that means from the bottom of the Ferris wheel to the top of the Ferris wheel, it is 50 feet. Okay? All right. So remember your observations. After 15 seconds of the Ferris wheel ride, this went from the bottom to this position here. If we were to break down this Ferris wheel into the 8 positions shown here, where we have the 4 cardinal directions and then halfway in between as well, this would be in the 3rd position, counting clockwise. So if the first position is at the bottom, we have the 2nd position, 3rd position, and first, second, and 3rd position here. Okay, so this would be like the 0 starting point, and then 1, 2, 3. Okay, so then this is our 3rd position after 15 seconds. So we can deduce that between each position, there must be 5 seconds. Okay, now if there are 1, 2, 3, 4, 5, 6, 7, 8 positions total, and it takes 5 seconds to move from position to position, it takes for one full rotation around the Ferris wheel, it takes 8 times 5 seconds or 40 seconds. So the period, the length of one rotation is 40 seconds. Okay? So if I were to sketch one cycle of this Ferris wheel, well, I know that the starting height, we're at the bottom. So we're at 9 feet. It's 50 feet in diameter, so the highest point that will be all the way at the top of the Ferris wheel is going to be a distance from the ground, 59 feet, because that's our 50 feet diameter plus the 9 feet above the ground. So that maximum must be 59 feet. So these are our y values. We're measuring the height above the ground in feet. Okay, our x-axis is time in seconds. Okay. I also know that at 0 seconds, we're at the bottom, and then also at 40 seconds, the end of our cycle, we're at the bottom as well. So I can go ahead and plot those points. This ride moves at exactly the same pace throughout the whole ride, so then exactly halfway between 0 and 40, we're at a maximum. In between that, we must be right at the middle of the ride. So at 10 and 30 seconds, we must be at the middle. And so now we have to determine what is that middle value. So looking back at the diagram here, this is this position and this position over here. So that would be position 2 and position 7. Okay, or 6, I'm sorry. 2 and 6. So then what is the height from the ground? Well, it's got to be that it's 25 feet. That would be the radius of the Ferris wheel, plus the 9 feet. That's going to give us 34 feet. Another way we could do this is take our max plus our min and divide it by 2, and that's going to give us our midline. Okay, so let's go ahead and sketch this. This is a periodic function, and it can be modeled using sine or cosine. So we've got this graph here. Okay. I'm going to draw the arrowhead on the right-hand side of the graph because the ride continues beyond 40 seconds, but it does not continue on the left-hand side because the ride starts at 0 seconds. We can't have negative time. Okay, so number 3, find the position of the red car at the end of the ride. So remember, this is 300 seconds. So if this is a function, we'll call this h of x. Actually, let's call it h of t because it's the height. It's the height per unit time. So then what we're looking for is h of 3 minutes. Okay. Well, remember our units are in seconds, so I need to know how many seconds is 3 minutes. So I know that each minute is 60 seconds. So therefore, we're looking for h of 180. Okay? All right, so I know that every 40 seconds, we're at a minimum. So at 40 seconds, we're at 9 feet. At 80 seconds, we're at 9 feet. At 120 seconds, we're at 9 feet. And at 160 seconds, we're at 9 feet. Okay, so at 160 seconds, we're at a minimum. 180 is 20 seconds greater than 160. So we're going to move forward in the cycle 20 seconds later. And at 20 seconds later than 160, we're at a maximum of 59 feet. So we know that h of 180 seconds is 59 feet. And so what does this represent? This is at the top of the Ferris wheel. Okay. Let's see if we can model this using an equation. Okay, so again, we're going to write this as a function, the height as a function of time. So h of t is equal to, well, we'll start with our amplitude, our a value. So to find our amplitude, remember it is max minus min divided by 2. So max is 59 minus our minimum of 9 is 50 divided by 2 is our amplitude, 25. So max minus min over 2. And actually, I'll go ahead and write that too. Amplitude is max minus min over 2. So we have 59 minus 9 over 2, 50 over 2, or 25. Okay. Now we have to determine whether this is sine or cosine, in positive or negative. Well, if we're starting at a minimum, and we're going up, passing through the midline, hitting a max, back to the midline, and ending at a minimum, this must be the negative cosine function. So I'm going to write negative cosine. My period, so here I know that the period is equal to 40 seconds. And that must be equal to 2 pi over b. Solving this equation for b, I get b is equal to 2 pi over 40, which reduces to pi 20ths. Okay. We have our variable x, and then we don't have a horizontal shift. We're starting at x equals 0. Or I'm sorry, our variable's not x, it's t. There we go. And we don't have a horizontal shift, so that's the end of the argument of the cosine. And then finally, our midline, or our vertical shift, is equal to the max plus the min over 2. So if our max is 59, our minimum is 9, we can add those two and divide by 2. So 59 divided plus 9 is 68. Divided by 2 is 34. And remember, that was our midline. We can see that from our graph. Okay, so then our vertical shift is plus 34. And this is the equation that models this motion in the Ferris wheel. So how many complete spins do you think that the red car will take on this ride? So I know that it takes 40 seconds for one complete spin. We start at the bottom, end at the bottom. So it takes 40 seconds. So how many times in 3 minutes can we do 40-second spins, or one full rotation around? Well, I can take my total 3 minutes, or 180 seconds, and divide it by 40, and that's going to give me 4.5. Okay? So if I do my total 180 seconds divided by 40 seconds, that equals 4.5 rotations, and we're asked for the number of complete spins, so that tells me that there are 4 complete spins. All right. So we can use sine and cosine to model any of this periodic behavior, any of the cyclical or oscillating motion here. We can write a sine or cosine equation to model that. And we can use these equations to extrapolate or interpolate data, meaning if I wanted to know if this was a 20-minute ride, first of all, that would be a really long ride, but also then how, if it's 20 minutes, where would the red car be after, say, 20 minutes, or even like 15 minutes, something like that. I can extend the data beyond what is given. Okay? So we're going to get a whole lot of practice on this in class, so we'll see you tomorrow. Have a great day.